This is DetectMare, a TryHackMe detection engineering room built around a full espionage intrusion that generated exactly 0 alerts. The incident is already known. Our job is harder in a different way. Prove why 5 detections failed, rebuild them against real Splunk data, and make each one survive both the customer environment and attacker variation. By the end, we will have 5 deployed Sigma rules, a 6-step attack timeline, 10 verified room answers, and a better definition of a good detection than simply matching one process name. The operating loop is consistent, but the reasoning changes in every pull request. We read the broken Sigma rule, compare it with the incident report, search the real data, identify legitimate lookalikes, tune only what the evidence justifies, then let the automated red team tests attack our assumptions. We will explain each new log source and each new command when it first appears. Later chapters will refer back instead of repeating the same lesson. This room is designed around 2 web applications. Splunk contains the collected environment telemetry. The GitHub-style detection as code application contains the rules, pull requests, and pipeline. No evidence download is required. A local browser, Kali Firefox, or the attack box browser can all work, as long as both lab URLs open. The important choice is not the operating system. It is keeping Splunk and the DAC applications side by side so we can move from evidence to rule and back without losing context. Every search begins in the DAC lab index. In Splunk, an index is the searchable data store that narrows the event set before we add behavioral conditions. We will usually pipe the result into table so the screen contains only the fields needed for the current question. Then sort by time when chronology matters. The table command is a presentation step, so it belongs near the end of the search. Once that pattern is established, later chapters will focus on the new fields instead of reteaching the pipe. Detection as code treats a detection rule like software. Version it, review it, test it, and deploy it through a controlled pipeline. The repository is the source of truth. Sigma gives us vendor-neutral detection logic. The converter produces Splunk SPL. Environment validation measures true positives, and false negatives against the known incident. The automated red team test then checks whether an attacker can keep the same technique while changing the easy details. Task 1, Case Briefing. Select the roll card, then open the Active Case tab in the TSS Operations Hub. The client is the Meridian Defense Research Institute, a government research organization. Tom Becker is the lead analyst, and the case is marked High Priority. The activity is assessed as consistent with APT21, also tracked as Zhenbao, Hammer Panda, or TEMP Zhenbao. A propulsion lab engineer opened a spear phishing attachment. A NetTraveler-style loader established the foothold. The operator mapped the domain, harvested credentials from memory, replayed stolen hashes onto classified file servers, and staged weapons program designs into encrypted archives. The crucial fact is operational, not historical. The estate generated no alert during the entire chain. Tom's message tells us not to make cosmetic edits. Jordan Blake has opened 1 pull request per detection gap, and every rule needs real tuning. The incident report lives under threat-intel. The customer-specific benign behavior lives under docs. That second file is essential. A rule can be technically valid and still be operationally useless if it alerts on approved automation all day. The other hub tabs establish the fictional operating environment. TSS fields 6 disciplines: incident response, threat hunting, digital forensics, malware analysis, threat intelligence, and detection engineering. The team page lists 1 specialist in each discipline. The All Cases page also links the earlier silent transfer case. This context is useful for continuity, but it does not change the detection logic, so we will keep it concise. Task 2, Tuning Detections. Before opening pull request 1, inspect the repository. The root contains the CI workflow, environment documentation, 5 Sigma rules, the threat intel report, and the README. This is the room's evidence hierarchy in file form. The incident report tells us what the attacker did. The environment file tells us what legitimate activity could look similar. The rule file tells us what the current detection actually matches. Open the incident report and read the 6 phases in order. Initial access is Office launching CMD, MSHTA, or Reg SVR 32 toward 45.77.12.9. Execution abuses run DLL 32 or Reg SVR 32. Discovery uses native commands. Credential access targets LSA-SS. Lateral movement produces a network logon with NTLM and key length 0, followed by service creation. Staging compresses sensitive CAD files with password-capable archive commands. Discovery has no open pull request. The other 5 phases do. Please try to remember these because in later chapters I should link back instead of re-summarizing it. Now open environment routines. The named exceptions are not generic allow lists. They are precise customer-owned routines: Office telemetry, finance automation, software deployment, CAD licensing, EDR and crash handling, PAM, legacy NTLM, cluster logons, backups, patching, and SolidWorks autosave. The rule should exclude only a routine we can identify with enough context that an attacker cannot cheaply borrow one trusted file name and disappear. Pull request 1 targets spear phishing attachment execution. Before running the pipeline, we need to inspect what the proposed rule actually detects. The current rule matches Microsoft Word spawning Office telemetry agent. That is already suspicious from a detection design perspective because it describes one exact process pair rather than the broader behavior mentioned in the pull request. The environment documentation confirms the larger problem. Office Telemetry Agent is the Institute's signed Office Telemetry helper. Any Office application may launch it during logon. The rule is therefore detecting a trusted environmental routine instead of the malicious Office child process described in the incident report. Alrighty, let's check our first run now. The first validation run confirms the mistake. The rule produces 0 true positives, 1 false positive, and 1 false negative. It alerts on the legitimate telemetry helper while completely missing the actual attack event. Let's check the first question. What is the doc file opened by the infected user? The incident report gives us the behavior family: Word launching CMD, MSHTA, or Reg SVR 32. We search for WinWord as the parent and those 3 children. Parent image identifies the creator process. Image identifies the new process. Parent command line will also preserve the document path, which is exactly what question 1 asks for. For the question, the result is on ResearchEng at 842. The user is research_m.okafor. WinWord opened hypersonic test schedule, then spawned CMD. CMD used certutil with URL cache, split, and force options to retrieve u.dat from 45.77.12.9 into the user's temporary directory. Certutil is a legitimate Windows utility, but here its network download behavior and Office parent make the chain suspicious. So with that said, the answer is hypersonic test schedule. The environment file says an approved Excel macro launches cmd.exe to run month-end report bat. That overlaps our planned Office parent and command shell logic, so we verify the routine before writing a filter. The search returns 4 monthly events. In each one, Excel opens the approved month-end template XLS, and CMD runs the approved batch file from the Research IT automation path. This is enough context for a narrow exclusion. Alrighty, let me show you my first revision code. The first revision broadens the parent family to Word, Excel, and PowerPoint, and the child family to CMD, MSHTA, and Reg SVR 32. It also excludes the documented finance automation, when Excel launches CMD and the command line contains month-end report BAT. This is still a deliberately loose first revision. We will use the pipeline to determine whether it is robust enough. Environment validation now reaches 100%, with 1 true positive and 0 false positives. The rule detects the observed incident without alerting on the finance events present in Splunk. However, this only proves that it fits the current data set. It does not prove that the rule survives attacker variation. The automated red team test passes only 2 of 5 attempts. Alrighty, let's check in the details. What's the problem with our little buddy? It misses Excel spawning encoded PowerShell because PowerShell is outside the child list. It misses Outlook spawning MSHTA because Outlook is outside the parent list. The last failure is more subtle. An attacker can rename a payload to month-end report BAT. A filter that trusts only the script name lets the attacker borrow the exception. The fix is to bind the filter to the real Excel template and the real automation path together. The final rule adds Outlook to the parent family and PowerShell plus PWSH to the child family. The finance filter now requires 4 facts at once. Excel is the parent command line contains the approved month-end template, CMD is the child, and the command line contains the approved Research IT batch path. In Sigma, ends with, contains, and starts with are field modifiers. They express where the wildcard belongs when the rule is converted to a backend query. All 4 pipeline stages now pass. Environment validation is 100% with 1 true positive and 0 false positives. The automated red team test passes 5 of 5. Approve the pull request. Merge it and read the deployment comment. Copy. Now paste. And voila. Let's check out pull request number 2. Pull request 2 targets signed binary proxy execution. The original rule looks for run DLL32 plus a program data path. The first validation produces 0 true positives and 5 false positives. Program data is not inherently malicious, and the research deployment tool legitimately invokes run DLL against packages stored there. The issue tracker states the coverage gap plainly. The rule only flags the deploy tool. Question 3 of 10 asks for the file name of the internal tool that may cause false positives. Search the exact behavior the original rule matches. 5 events appear. 4 are packages launched by the service account through cprogram research deploy.exe. 1 is Windows error reporting through SVC host. The internal deployment file name is therefore researchdeploy.exe. So the answer is researchdeploy.exe. The CAD license checker is another documented exception. It uses regsvr32 against a .dat file in appdata local temp identified by the string license check. The search returns 4 events from SOLIDWORKS. That means our final rule must cover regsvr32 and appdata without alerting on this named licensing workflow. At 9:06, MSHTA reaches 457712.9 for CFG, then spawns regsvr32. regsvr32 uses the /iurl option to retrieve s.set and references scrobj.dll under program data. MITRE ATT&CK describes regsvr32 as a trusted signed binary that can execute remote scriptlets while avoiding normal application control expectations. The suspicious behavior is the signed proxy binary plus a non-standard path plus an uncommon payload type, not the signed binary alone. The final selection has 3 independent pieces. The image must end with run DLL or reg svr. The command line must contain app data or program data. It must also contain .dat, .tmp, or .sct. We then remove only 2 trusted workflows, researchdeploy.exe, operating on the research IT package path, and reg svr commands containing license check. The .sct value matters. An intermediate version containing only .dat and .tmp produced 0 true positives because the real event used s.sct. The corrected rule finds 1 true positive with 0 false positives and passes 3 of 3 red team tests. Approve and merge the pull request. Nice, we got the flag, copy it, paste it there, and question 4 is done. Alrighty, let's see the next 2 questions before we move on to pull request number 3. Seems like we need the username of who's executed the LSASS dump and the pull request 3 flag. So check out the pull request now. Pull request 3 targets LSASS memory access. The original rule matches werfault.exe opening lsass.exe. Let's see what happens when we run it. The environment file says that exact crash handling behavior is legitimate when the access mask is 0x1410. Validation returns 0 true positives and 4 false positives. This rule uses sysmon process access telemetry. Sysmon event ID 10 records one process opening another process, including source image, target image, access rights, and call trace. It is powerful for credential theft hunting, but it is noisy without context. The original rule is failing because it treats the documented where fault crash handling routine as credential theft. We already know that the environment validation found 4 false positives, so we do not need to waste time proving the same failure a second time. Instead, we remove werfault from the search and review every other process that opened LSASS. This gives us the relevant comparison set in one view. Research PAM, Research EDR, and Task Manager are present because they are documented environment routines. The standout event occurs at 10:20 on March 11th. Its source process is run DLL. It opens LSASS with granted access, and its call trace contains both COMS-VCS and an unknown memory region. That is the meaningful combination. The incident report describes the COMS-VCS mini-dump technique, while the unknown region supports the unsigned or untrusted call trace context. We are not saying every non-werfault LSASS access is malicious. We are identifying the one event whose process, access level, and trace align with the reported attack. Question 5 asks for the username the attacker used to execute the LSASS dump. The table's user value is not translated, so that field is not the answer. We need the raw sysmon event. So let's go to Events, click Verbose, and look for our date stamp. And here we go. Sysmon event ID 10 records one process accessing another process. In this event, the source process is runDLL, the target is LSASS, and the raw record preserves the actual source user fields. So the answer is Okafor. Let's put it in. The investigation gave us the behavior we actually need to detect. The target is LSASS, but LSASS access alone is not enough. Legitimate crash handling, endpoint security tooling, and the PAM Vault agent can all open it. The stronger signal is the call trace. Memory dumping activity can involve DBG help, DBG core, or COM services. An unknown entry is also relevant because it represents an unrecognized memory region in the trace. We will detect LS-ASS access combined with one of those suspicious trace indicators, then exclude only the documented benign routines. This avoids betting the entire detection on one granted access value. The where fault exception remains deliberately narrow. We exclude it only when it is where fault accessing LSASS with 0x1410, which is the documented crash handling pattern. We also exclude the named Research EDR and Research PAM installation paths, rather than broadly excluding tools or call trace modules. All right, enough talk, I guess. Let's run the checks. The final LSASS rule: passed everything, approve it, merge, and copy the flag. Alrighty, check out the next questions. We need the pass the hash authentication timestamp and another flag. So check out our pull request number 4. Pull request 4 begins with security event ID 4624 and logon type 10. Event 4624 means an account logged on successfully. Logon type 10 is a remote interactive logon, typically remote desktop, not the network logon pattern in the incident report. Let's run the checks. Validation returns 0 true positives and 16 false positives. Let's go back to our good old Splunk. The original rule uses logon type 10, but the incident report gives us a more useful fingerprint for pass the hash. Successful network logon, NTLM authentication, and a key length of 0. So rather than spending time on the wrong logon type, we search directly for the behavior described by the incident. Key length 0 is suspicious here, but it is not automatically malicious. The result set contains 2 documented exceptions. First, SVC_cluster authenticates between the 2 classified file servers as part of failover clustering. Second, SVC_MES authenticates from MES Legacy 01, which still relies on NTLM. One event does not fit either routine. M.Okafor authenticating to FS classified 01 from Research PC 44 at 10:40 a.m. That is our pass the hash event. Oh wait, I have to remake its format. Good. All right, let's replace the detection block with this first revision. It detects the pass the hash logon and removes the known benign MES and cluster traffic. The rule now finds the authentication event, but validation expects 2 malicious events. The missing event is the remote service installation that followed the hash replay. We can go directly to the suspicious service path from the incident report. Event ID 7045 at 10:43 created Win Help Service from C program data intelnt.dat 3 minutes after the pass the hash logon. So now we add the program data service selection to the first revision. This should detect both known malicious events, the pass the hash logon and the Win Help Service installation. Environment validation is now fully successful because the rule finds both known attack events. Open the automated red team test next. One of 2 tests passes, but the other bypasses the program data path check by installing a service that launches cmd.exe and PowerShell from another location. So we keep the program data selection for the observed attack, then add a second service pattern for that bypass. The final rule detects either the filtered pass-the-hash logon, a service launched from program data, or a service command that contains both cmd.exe and PowerShell. The final validation remains at 100% with 2 true positives and 0 false positives. This time, the red team test also passes both bypass checks. This is coverage for both sides of the attack chain, but it is not a temporal sigma correlation rule. The rule alerts on either event type. An analyst can connect the logon at 1040 and the WinHelp service installation at 1043 using the shared host and timeline. Let's approve and merge it. Put in our flag. Let's see our last 2 questions. In which folder should an attacker place a malicious binary to make it look like a legitimate backup routine? And we need the last flag too. Now check what is inside pull request 5. Pull request 5 covers archive staging for exfiltration. The original rule alerts whenever the image ends in 7z. That is too narrow and too noisy. The initial validation reports 0 true positives and 13 false positives. A real attacker can use a different archive utility or rename the executable entirely. Instead of searching every archive utility separately, we can go straight to the sensitive design extensions named in the incident report. This single search also shows the legitimate backup context needed for question 9. The results include legitimate nightly backups launched by researchbackup.exe as service backup, writing archives under dbackups nightly. They also include SOLIDWORKS autosaves under sw_auto backup. But the 1050 row is different. cmd.exe launches rar.exe from Okafor's temp folder. Its command uses -hp to password protect C users public d.rar while collecting classified SLD PRT files. The behavior is the signal, sensitive design files plus archive or password semantics, not the name 7z.exe. So the answer to our question should be backups/nightly. Let's go back with the newly acquired informations to our poll number 5. Now replace the file name only rule with behavior-based logic. The rule requires a classified design extension and an archive indicator. It excludes only the 2 documented routines that can match this behavior, the research backup job and the SOLIDWORKS autosave. Personal photo archives do not need an exclusion because they never match the sensitive design file selection. Alright, before I run our last check, please like, sub, and comment if this video helped you. Also, stay until the end, where I will summarize our whole lab. The rule now detects the real rar.exe archive event without relying on its file name. Environment validation reaches 100% with 1 true positive and 0 false positives. The automated red team test passes all 3 bypass checks. Approve and merge pull request 5. This deploys the final archive staging rule. Put our newly achieved flag in. The 5 PRs now form one evidence-backed view of the intrusion. This timeline separates the initial workstation on the left from the classified server on the right. At 8:42, Okafor opened hypersonic test schedule on Research ENG 1.4. WordSpawn CMD, which used certutil to download u.dat from 45.77.12.9. At 9:06, MSHTA launched reg SVR32 to retrieve the SCT payload from the same attacker infrastructure. At 10:20, Run DLL accessed LSASS through a COM SVCS call trace. At 10:40, the attack moved to FS classified. The server recorded an NTLM network logon for Okafor with key length 0. At 10:43, the attacker installed winhelp from C program data intelnt.dat. At 10:50, rar.exe staged the classified design files into a password-protected archive. The original rules failed for 5 different reasons. PR1 selected a known benign Office telemetry child instead of suspicious Office-spawned processes. PR2 treated the program data path as malicious instead of assessing the signed binary, payload context, and known deployment routine together. PR3 selected routine crash handling, then briefly overfit one LSA SS access mask. PR4 initially used the wrong logon type and then detected only the authentication half of the attack. PR5 trusted the archiver file name, even though the real attacker used rar.exe, not the benign 7-zip process. The final rules instead use behavior families, narrow environment-specific filters, and automated testing against realistic attacker variation. A production detection needs 3 kinds of proof. First, it must catch the known attack. Second, it must avoid the legitimate routines identified in the actual environment. Third, it must survive reasonable variations of the same technique. Environment validation checks the first 2. Automated red team test checks the third. Passing Sigma syntax alone proves only that the YAML is valid, not that the detection is operationally useful. DetectMare is complete. 5 rules are deployed, all 10 Task 2 answers are verified, and the incident is no longer invisible to the same brittle assumptions. The practical takeaway is simple. Detection engineering is not process name matching. It is evidence, environment, and adversary behavior expressed as testable logic. Hope you enjoyed this video. Come back later for more. Bye-bye.